Ayubowan students, and a very warm welcome. It's great to have you with us for this important Grade 10 science lesson.
You're here at Study Hub Sri Lanka, and today we're going to tackle a really key topic in physics, linear motion. Now, don't worry, by the end of this, you'll have a super clear understanding of how we describe things moving in a straight line. So let's jump right in.
So what's on the menu for today? Well, we'll start with the absolute basics, distance and displacement. Then we'll add time to the mix to understand speed and velocity. After that, we'll see what happens when velocity changes, that's acceleration, and finally we'll learn how to see the whole story with motion graphs. It's going to be great.
All right, let's get this show on the road. To really get a grip on motion, we have to start at the beginning. How do we even describe where something is and where it has gone? This is our starting line.
Okay, I want you to picture this. You're walking from your home, which is point A, to your school at point B. Now, as you can see, you could take a few different routes. So let me ask you, which path is the correct one? Well, funny thing is, in physics, the answer really depends on what you're trying to measure. And this simple question gets us to our first two big ideas.
And here they are. First up, we have distance. This one's easy. It's just the total length of the path you actually walk. Every single step, every turn, it all adds up. But then we have displacement. This one's a bit more specific. It doesn't care about the journey, it only cares about the start and the finish. It's the shortest straight line path between them, and, this is super important, it includes the direction.
So distance belongs to a group of things we call scalar quantities. The best way to remember scalar is to think of a scale. It just gives you a number, a magnitude, or size. You know, like 10 kilometers or 30 minutes. There's no direction, just a value. Simple.
But displacement, now that's what we call a vector quantity. Vectors are awesome because they give us more information. They don't just tell you the magnitude, the how much. They also tell you the direction, the which way. So you wouldn't just say 5 kilometers, you'd say 5 kilometers east. That little bit of extra information, the direction, is what makes it a vector.
Okay, theory is great, but let's make this super clear with an example, one you'll see in your textbook.
So a child walks from home, goes 100 meters, takes a turn, walks another 400 meters, and then turns again for the last 200 meters to school. First things first, let's figure out the total distance they walked.
All right, let's do some quick math here. We just add up all the parts of the journey, right? So we've got 100 meters plus 400 meters plus 200 meters, and that gives us a grand total of 700 meters. Easy. Remember, for distance, every single step counts.
Okay, so we know the distance is 700 meters. But what about the displacement? Remember the definition. It's the shortest straight line distance from the start to the end. So for a moment, let's just ignore that winding path the child took. If you could fly in a straight line from home to school, how far would that be? And the answer is 500 meters. If you were to draw a straight line from the start point to the end point on that map, it would measure 500 meters. So, see the difference? The child walked 700 meters, but their final position is only 500 meters away from where they started. That's the key idea. Distance is the whole path, displacement is just start to finish.
Great! So now that we know how to talk about where something is and where it's gone, let's bring in a new ingredient, time. This lets us ask the next question, which is, how fast are we moving?
And that brings us to speed and velocity. I bet you're already seeing the pattern here, right? Speed is our scalar friend. It just tells you how fast you're going. You find it by dividing the distance by the time. And velocity? Yep, that's our vector. It tells you your speed and your direction. And we calculate that using displacement divided by time. Same pattern as before.
Let's look at what we call uniform speed. That just means the speed is constant, it's not changing. Check out this table. For every single second that goes by, the object travels exactly 3 meters. It's steady, predictable, moving at a constant 3 meters per second.
But this is a bit more like real life, isn't it? Non-uniform speed. In the first second, it moves 3 meters, okay? But in the second second, it only moves 2 more meters. Then it speeds up and covers 4 meters in the third second. See? The speed is all over the place. It's changing. So that leads to a great question. What do we call it when velocity itself is changing? This brings us to our third big idea for today, the one that describes speeding up, slowing down, and even just changing direction. Let's talk about acceleration. So, acceleration is all about the rate of change of velocity.
The best way to think about it is pressing the gas pedal in a car. When you do that, your velocity changes. You speed up. That change is acceleration. And because velocity is a vector with direction, acceleration must be a vector too. And it's pretty straightforward. When your velocity is increasing, when you're speeding up, we call that positive acceleration. When your velocity is decreasing, like when you hit the brakes, we call that negative acceleration. You'll also hear that called deceleration. Same thing. Phew, we've covered a lot of ground. New words, new formulas. But what if I told you there was a way to see an object's entire journey, all the speeding up and slowing down, in just a single picture? Well, there is. Welcome to our final section, motion graphs. This is where it all clicks into place. Now, listen up because this is the secret key to everything. When you're looking at a velocity time graph, there are two golden rules. If you can remember these two things, you can solve almost any problem. Rule 1, the steepness of the line, what we call the gradient, tells you the acceleration. Rule 2, the total area underneath the line tells you the total displacement. That's it. So what do we do if the area under the graph is a weird, complex shape? It's actually really simple. You just break it down. You divide that big, weird shape into smaller, simple shapes that we know how to work with, like triangles and rectangles. Then you just find the area of each little piece and add them all together at the end. So let's try it with our example. We can break it into 3 shapes. The first bit is a triangle, and its area is 45 meters. The middle part is a nice, easy rectangle. Its area is 90 meters. And the last bit is another triangle with an area of 22.5 meters. So what do? We just add them up. 45 plus 90 plus 22.5 gives us a total displacement of 157.5 meters. See how powerful that is? You know, we've done an amazing job today. We've learned the language to describe motion, we can define it, we can calculate it, we can even draw a picture of it. But this leaves us with one last really big question. We know acceleration is a change in velocity, but what actually causes it? What makes something speed up or slow down in the first place?
And that is a fantastic question that we are going to explore in our very next lesson when we start talking about forces. You all did a brilliant job today. You really did. Thank you so much for joining us here at Study Hub Sri Lanka, and I can't wait to see you for the next one.